Shut up. If you talk now, it's on. I have video evidence. Okay, so I want to start by just a reminder about time commitment in this class. We had, so I just gave you back a quiz that, the homework assignments always say, it always says start by reading the notes, going over the example problems, okay? And that's a crucial part. You can't learn this stuff without remembering the stuff that I say in class. So that's an important first step in doing the homework. And the second thing is it tells you to go back over some problems that the solutions are posted for. Okay? The last quiz, the one on Friday, both questions on the quiz were questions that the solutions were posted for. Okay? So there's no reason not to get those right, except just not spending the time that you need to do to go through those solutions. You know what I mean? It wasn't a matter of not being able to figure it out. It's just you need to do what the assignments say, and so I thought I'd just start by reminding you the amount of time that is required outside of class in this class, in any college class. And I'm talking here about the minimums, okay, not the maximum amount of time commitment that you're expected to do for college credits, but this is the expected minimum. And I think in this class we can get by fine with you doing the expected minimum, but this is what you have signed on to do outside of class, okay? Commitment. Okay, so in addition to all the stuff in class, you need to be doing 10 hours a week of work. Okay, so this is how that breaks down. If you don't take any days off from this class, that's 1 hour 26 minutes per day. Okay, that's a lot, and that's if you don't miss any days, okay? Okay, look, I know a week is not a single word. I'm just not going to go back and erase it, okay? If you miss one day, which is pretty common, like you're busy people, then on those other 6 days, that's 1 hour 40. If you miss 2 days, that's 2 hours. Okay? If you miss 3 days and you're going to do it all in 4 days a week, which, like I said, I know like you guys have a lot of commitments and stuff, but you have to make up those days you miss, and that's 2.5 hours a day if you do it 4 days a week. And if you spend this amount of time, you have time to read the class notes, go through the example problems and make sense out of them, go back over the old assignments that I've posted the solution for, and work on the new assignments. Okay? But if you don't do this, there's this class, every college class is designed around expecting a time commitment in this ballpark. You know what I mean? So if you're not spending this amount of time, it's not my decision. There's just not much I can do. These classes are designed for that kind of time outside of class. Okay? So that's all. It made me a little nervous to look at those quizzes and see the scores overall that people got based on stuff that the solutions were posted for. It wasn't an understanding thing. It was just a thing about not doing what I asked you to do. Okay. Jake. Also, I think today we're going to get the textbooks, so I want to say something about using the textbooks. The textbook is not a replacement for any of the stuff that I'm asking you to do. You know, like, for your own good, don't replace the time that I ask you to review the class notes with reading the textbook, okay? And here's why. Because the class notes, as I've designed them, are set up to make you understand the problems that are going to be on the quizzes, the exams and whatever. The person who wrote the textbook is thinking in a different way, presenting stuff in a different way. And so it can help you. I mean, it's great to use other sources, but you need to do that in addition to spending the same amount of time on the class notes that I give you, okay? The class notes that I give you are the ones that are designed to help you with the problems in this class. The way the book stuff is written, that's designed for another way of thinking about this material. Okay? So for your own good, don't replace the stuff that I tell you in class with the textbook stuff. It's 100% guaranteed going to make you more confused in this class if you do that. Okay? Yeah, it's a great resource though if you want to go through all the stuff that I do and then spend some extra time fleshing out your understanding of the material. Okay? All right. What were we talking about last time? That's not fair. What? Oh, what did she say? Oh, yeah, you're right. Yeah. Okay, so here's where we are. So we first started talking about kinematics. What's kinematics about?
Well, it's applied to an object.
That's kinetics. So yeah, kinematics was the first stuff. Yeah, so this is, you can think of kinematics as just describing the motion. And we were doing it of particles, you're right. Although later we'll talk about kinematics of rigid bodies and stuff. This is just describing motion. So what are the quantities involved in kinematics? What are the physical quantities that we use for kinematics? Give me one. The person who gives me the first one doesn't have to give me any more. So someone give me the easy one and then you're done.
Time.
Yeah, good job. See, that's a good strategy. Now you guys have to come up with the harder ones. Yep. Yeah, so in general, well, just position, right? Yep. And that's a vector. What else? Two more. Yep. And acceleration. Okay. So kinematics is just about these things, these four things. Now we're on to kinetics. Whoops. Kinetics. And kinetic, yes?
Isn't velocity just position relative to time and acceleration just velocity relative to time? So couldn't you just write those as just time and position, or should you write them as all four?
You should think of them as four different things because at any given instant, those four things are independent of each other. If you happen to know one of them as a function of time, then you can write the other two in terms of that. But there are a lot of cases where we don't know them as functions of time, we're just given them. And in that case, you have to have all four of those. Okay, so kinetics is mainly, so we introduce what two additional quantities?
Mass and force.
Yep, good. So mass, m, and force. Yeah. No, that's totally right.
Okay.
Yeah. Never doubt yourself again. Okay. And mainly, kinetics is about Newton's second law. We'll talk about Newton's first law, Newton's third law a little too, but mainly it's the second law. And that one says that if you add up all the forces on a body, that's equal to the mass times the acceleration. And so this is new for this topic. This is new. But this acceleration, to calculate this acceleration, we still can do all the stuff that we did in kinematics. So whatever we know from a kinematic analysis, we can use here. Often the way that's going to come up is in, like, what's the type of motion where we knew the most about the acceleration when we were just doing kinematics towards the end? Circular motion. We knew a lot about the acceleration, right? And so this is going to come up often in circular motion problems where we're going to figure out some stuff about the forces, but we're also going to be able to figure out some stuff about the acceleration just based on doing the kinematics, okay? So I want you to just remember that this acceleration, basically, this acceleration that's on the right side of Newton's second law is the same acceleration we've been dealing with all the way up until now. Any kind of kinematic analysis you can do of the problem, you can use that in this acceleration. The new stuff, the free body diagrams and all that, is mainly about representing the left side of Newton's second law, okay? All right. Pushing contact. Okay, so we have, here are the force types. There are 5 of them. What's the first one? I don't remember what order I went in. Okay, weight is one of them, sure. Yes. The second one is pushing contact. Yep. And now those are the 2 that we've done. I'll start with one example of pushing contact. And then, yep, the next one is pulling contact. Next one, friction. And then the last one, yep, spring forces. Okay, so we're working our way through this list. Okay, so as an example, let's say we had 2 little carts rolling along the ground. And let's say there's a 40 Newton force applied there. Let's say this is 5 kilograms and 3 kilograms. And we want to know first what's the acceleration of the system. And second, what's the force vector applied on the 5 kilogram box by the 3 kilogram box. Okay, so to calculate the acceleration, this is going to be a theme we're going to see over and over again. the best way to do that is to isolate the whole system. So the chosen body is going to be the whole system of carts, of 2 carts. Okay, so let me pause. Oh no, are there markers in here? 2, 3. I should. Yeah, that'd be great. Thank you. So what I would like you to do is just try to remember how to draw a free body diagram when the system are these 2 boxes. Okay? Write it up on the board, and then I'll go through it. And if you can't remember how to do it, or it looks terrible or whatever, that's fine. I'm just trying to get us to work through this. I'm going to do the way that you should do a free body diagram of the whole system, and then we'll just talk about what are some common mistakes, easy mistakes to make. So, free body diagram of both. Okay, so I'm going to start out with an outline of the chosen body, which is this whole system. I don't really care if you put this much detail into it, but that's an outline of the chosen body. And then we're going to do, we're going to go in this order. We're going to think about the field forces applied to our chosen body. That's gravity. That would also be like electric forces or magnetic forces. In most of our problems, it's just going to be the weight. So that's acting down like this, and it has a magnitude of the mass of the chosen body. What's the mass of the chosen body? 8, yep, times g. So you could write that as 8g, or I think that's 78.48. And now we can just go around the outline looking for places where the outside world makes contact with our chosen body. Okay? So definitely over here, something's making contact with it, applying that 40 Newton force. And then there's contact at the wheels. There's 2 acceptable ways to do this. You could lump all the pushing contacts on all the wheels into a single force, or you could do it as a pushing contact on the 5 kilogram box and a pushing contact on the 3 kilogram box. I guess I'll break it up, but if you wanted to just call it one pushing contact, that would be fine. Later, when we're done doing particles, you'll have to do it on each individual wheel. Yep?
Shouldn't you also break up the HG if you're going to also be breaking up the ground pushing contact force? Or
You could do that, yeah.
Okay.
So I'm going to call this N5 and N3. And so, okay, so how did I come up with those directions? It looks like everybody pretty much did those directions right. A couple people missed those forces. That should say N3, not 3. But the way you need to think about that is when you're going around the outline, you're going around the boundary, and you get to the wheels, you think, okay, that's a pushing contact between the ground and the wheels. And since that's a pushing contact, we know that that force is first perpendicular to the surface, perpendicular to the ground, and second, it's toward the chosen body, away from the contacting body. So it's perpendicular to the ground, and it's pointing from the ground to the chosen body. Okay? Does that make sense? Okay. Now we get to this one, and now every place that there's contact between the outline and the outside world, we've represented, so we know we're done. Okay. So what are some things to look at So here are some common mistakes to avoid. In the free body diagram. The first one is don't draw any internal details. Just an outline. And that's because the key thing for the free body diagram is to know the forces that you're breaking up the universe into two teams. Your chosen team and everything else, you know? So you want to make a very clear boundary between what's your chosen system, your chosen object, and everything else. And that outline tells you, gives you the boundary between those two things. And then you want to represent all of the forces that the other team, the bad guys, the outside world, is applying to your chosen team. So that's why this boundary is really important. You're just going to apply that weight force, and you're going to go around the boundary looking for places that the outside world makes contact with your team. Yep.
So what things would qualify as internal details? I mean, I understand that the pushing force between the two would count, but would anything else?
Well, so first, when I say that, I'm just saying don't draw anything on the inside. So if, like, what if these carts had, like, flowers on them? And this one had a dragon inside. Okay? All that kind of stuff. Don't draw that stuff. All you want to draw is the outline. Okay? It's not a picture. It's just a diagram that separates your chosen part of the world from the rest of the world. Okay? The second thing is, okay, and for our purposes, the main internal detail that people were drawing that you don't want to draw is the boundary between the 5 kilogram box and the 3 kilogram box. So there shouldn't be any line between those two in your diagram. Okay? Like, see that one over there? That's those two first ones there are good examples of how that outline should look. Okay? Don't get a big head, though. The second thing that's related to this is, since we're only concerned about the forces that the outside world is applying to the inside world, we don't care about any forces that parts on our team, inside our chosen system, apply to each other. So the way this is coming up in this problem is you don't want to include the contact force or the contact forces between the 5 and the 3 kilogram boxes. Those are real forces, and if we isolated, say, the 5 kilogram box, which we're going to do next, then you do have to deal with the contact force with the 3. But the reason this boundary is such a key thing is because any forces happening between things inside the boundary, they don't matter to us. All we care about are the forces applied to our chosen system by the outside world. Yep.
Would friction count as an internal force or an external force?
It depends.
If it's wheels on an axle, then the friction is around the axle. but it's caused by the outside world. Would that be?
If there was friction in those axles, the way that that would come into this free body diagram is that those wheels wouldn't turn very much, okay? And therefore, the wheels would rub against the ground, okay? And so the friction that would matter to us would be the friction between the ground and the bottom of the wheels. The axle friction you're talking about would not matter in this system, okay? And then the last thing is don't draw any external objects. So in a couple examples, people drew the ground, okay? It seems like it makes sense to draw the ground, but don't put it in because all we're trying to do is be as clear as possible about what the boundary is. I see that. About what's the boundary between our chosen system and the outside world, okay? Again, we're not trying to make a picture. We're just trying to be real clear about that boundary. So, for example, don't draw the ground. Okay, so now we're going to use this to calculate in Newton's second law. So Newton's second law says, add up these forces. And the nice thing about the free body diagram is once you've done one, everything that appears in the free body diagram appears in the left side of Newton's second law and nothing else. So basically the free body diagram dictates to you what the left side of Newton's second law looks like. All right, so Newton's second law says we have a force vector of, well, this one's in the positive x direction, if I use that coordinate system. So what's that as a force vector? Yeah, positive 40x, 0y. This is in the positive y direction, so what's n5 as a vector? Well, actually, you're right about that, but we'll just calculate that as it comes up. So for now, all we're going to say is that's n5 in the positive y direction. However it appears in the free body diagram, that's how it appears in Newton's second law. So that's just going to be 0 n5. Okay? Then the weight, how does that appear? And what? Y, right? So that's plus 0, negative, I guess I'll write it as numbers, 78.48. And then this is the last one. What would that force vector be? 0 and 3, yep. And do we know anything about the motion of this? So I'll put the mass in here. And now to figure out the acceleration, remember acceleration is just kinematics. Do we know anything about the motion of this object?
No.
Well, we do know that its motion is all going to be along the surface, right? So we know there's not going to be any change in position or change in velocity in the vertical direction. Okay, so I'm gonna put a variable in to represent the horizontal acceleration, but not one for the vertical. We know that's going to be 0. Because all the motion is horizontal. Okay, so we get two equations. The first one is the x components of this equation. So 40 is equal to 8a. And so a is equal to 5 meters per second squared. Yep.
So we're discounting friction?
Yeah, we are in this one. And actually, anytime you see wheels in a problem, and it doesn't specifically mention friction, those wheels are meant to suggest that there's no friction. Okay, so now how do we take this variable value and express an acceleration vector based on that? Well, we've already decided what the acceleration vector is. All we needed to do was figure out what a was. Now we know what a is. And so now we can say the acceleration vector of this system is 5, 0 meters per second squared. Any questions about that? This is going to be, obviously, this is going to take a little while for this all to click, but you can sort of see how piece by piece you go through it, hopefully. Okay, that's part A. Part B is we're trying to figure out the force on the 5 kilogram box by the 3 kilogram box. The system that we chose for part A isn't going to work for this one. Why is that? Yep. Yeah, that's right, because in order to calculate that force, we need it to appear in the free body diagram, and those internal forces don't appear. So we're going to just have to isolate the 5 kilogram box. Okay, so go back up there and draw a free body diagram of the 5 kilogram box. All right, so here's the free body diagram for the 5 kilogram box. Outline of the 5 kilogram box. And then there's the field forces, which is just gravity. That's 5G, or 49.05. Then there's the force, that's a pushing contact with the wheel. So it's toward the chosen body, N5. Then over here, there's contact with the 3 kilogram box. So we want to represent the force on the 5 by the 3. So it needs some kind of variable. I'll call it R, but if you call it N1 or N2 or whatever, that works fine. And then over here, there's the, what was it, 40. Okay, so here are a few things to keep in mind. Okay, so first of all, so here are some common mistakes. Don't include any forces on outside objects. So I think a couple of people put the force that the 3 applies to the 5, but also put the force the 5 applies to the 3. We don't care about what forces are being applied to the 3. Okay? We only care what forces are being applied to the 5. And the second one is, so remember, how do you know when you're done? You know when you're done when you've included any field forces, the weight, and then you've gone around the boundary and represented every single time the outside world makes contact with that boundary. Okay? So if you're missing this R, this contact force from the 3 kilogram box, you've gone around the boundary, gotten to that point, there's contact with something, and you haven't represented it. Okay, so that's how you can always know whether you're done or not. Okay? So don't forget to represent every point of contact along the boundary. Okay, so now Newton's second law. What's the force vector? What's the force vector that the 40 Newton force? What's that represented as vector components? Yep.
40 over 0.
Yep.
Hold on, divided by 40 and then 0.
Yeah, positive 40, 0. And what's the force vector for the weight?
0, 49.05.
And it's in the negative y direction, so it's 0, negative 49.05. Okay? And then what's the force vector for N5? You don't have to calculate it. We're just, whatever variables appear here should appear in Newton's second law, and we'll calculate it there. So how would you represent this N5 as a vector?
0 and 5.
Yep, 0, positive N5, because it's drawn in the positive y direction. And then the last one, how would you represent this R as a vector? Negative R0, yep, because it's in the negative x direction. And all that is equal to the mass of our new chosen object times the acceleration. This time we know the acceleration. That's what we did in part A. So what did we get? 5. So the acceleration vector is 5, 0. And so now we have two equations. The x equation says 40 minus r is equal to 25. Since we're just trying to figure out that contact force, we're just trying to figure out the r that lets us find this force vector. That's the force on 5 by 3. Solve for r, and you get r is equal to 15. And so the force vector on the 5 by the 3, plug that in here, and it's equal to negative 15, 0 newtons. Any questions about that? Okay, let's do another example. So let's say you have this carousel thing, and you have a box on the carousel. And that box is being held in place by like a little arm that's pushing on the back of it. As this rotates around this way. Okay, and I'll use this coordinate system. You follow what I'm trying to draw there? The angular velocity is 5 radians per second. There's no angular acceleration. And the radius of this circle is 1.0 meters. If the box has a mass of 10 kilograms, what's the force applied to the box by the arm? And we're going to treat this like it's frictionless. So this carousel's made out of ice or something. All right, so why don't you take a few minutes and try to work through that one. So the way you're going to do this is you're going to break it up into a kinetic part with the free body diagram and the forces. That's the left side of Newton's second law. And then that's the kinetic part. And then the kinematic part is you're going to use the circular motion to calculate the acceleration. And then you'll combine those two in Newton's second law. So we have to break this problem. Everyone did great on this. You have to break this problem into an acceleration part. That's the kinematics of circular motion. And the force part, the left side of Newton's second law. The force part comes from the free body diagram. And so there's the box. Apply the field forces. That's just the weight. So the weight it has a mass of 10 kilograms, so this is 9.81 times 10. You can write that as 10g, or do the multiplication, and you get 98.1. And now we just go around the boundary looking for contact with the outside world. The ground is pushing up on it. And then the arm is pushing this way on it. Those are both pushing forces, and so you know the direction of those forces. I'll call that R. And so this tells us everything we need to know about the left side of Newton's second law. Okay? So now we have to go to thinking about the right side. Okay, so if the circle, let's think about the circle like this, and the x-axis is this way, whoops, the y-axis is up, the z-axis is this way. Which way is the velocity vector? I don't remember. Yes. Counterclockwise from above, yeah. So the velocity vector is like this. Is there any angular acceleration? It's not speeding up or slowing down, so there's no tangential acceleration. But there is a centripetal acceleration. There always has to be with circular motion. So that's pointing towards the center. And that's equal to the total acceleration. And the magnitude of the centripetal acceleration is omega squared r, which is 25 pointing this way. So what's that as an acceleration vector?
Negative 25.
That's right. It's in the negative x direction, so negative 25, 0. And now we have everything we need to put this problem together. We have the left side from the free body diagram, and we did the kinematics to know all we can about the right side. So Newton's second law says 0, negative 98.1. Plus 0n and what's this r as a vector?
Negative r over
That's right. It's in the negative x direction, so that's negative r, 0. Add up those forces, and that's equal to the mass times this acceleration vector we just figured out. This one here is the force vector on the box by the arm. So we know what that is as soon as we figure out what this variable r, the value of this variable r. So the first equation says negative r is equal to negative 250. So r is equal to positive 250. And so the force on the box by the arm is equal to, plug 250 into this force vector, and you get negative 250, 0. And so it can hold it on. See? Science.
Well, yeah, I was just wondering where the force is coming from. I realized like halfway.
Oh, okay, okay.
That it's like force of it pushing back on it.
Any questions about that? It looked like you guys did that one quite well. Okay, so the next thing we have to talk about is pulling contact, pulling force. And mainly we're going to think about these in terms of cables.
Okay. I have a quick question
Yeah.
about the last one that we did with the. Where did we account for the when we were finding the force applied to the 5 kilogram box thing by the 3 kilogram one? Where did we account for the mass of the 3 kilogram box?
That we only accounted for that when we were isolating both of them together.
Oh, okay.
Once we were, the term free body diagram comes from the fact that you separate your chosen object from everything else. All there is that you care about is your chosen object, and then the forces applied by the outside world to your chosen object. And so when we isolated the 5 kilogram box, we didn't care at all about. Yep.
Got it.
Any other questions right now? All right. So a pulling force, for example, if you have 2 carts one and 2, and say you have a 50 Newton force or something pulling on that one. The force that the cable applies to box 1 is a pulling force. It's also true of the force that the cable applies to box 2. All cables can do is pull. What happens if you try to push with a cable? It's just noodles, you know. Okay, so if you have a pulling force, so the pulling force, here's what we know about it. The pulling force direction first, it's parallel to the cable. And second, okay, so remember, if something's pushing, the force is toward the chosen object, away from the contacting object. Pulling is the opposite of that. So a pulling force is away from the chosen object, toward the contacting object. Okay, so in the example above, I'll do a free body diagram of cart 1 and a free body diagram of cart 2. So box 1 has a weight force. I'll call it M1G. And then the ground is pushing up on it. I'll call that N1. And then the cable is pulling on it. So that's a force vector parallel to the cable, away from the chosen body. And we have to label that, I'll call it T for tension. What about the 50 Newton force? Well, when you go through this process, you apply the weight, and then you just go around the boundary looking for contact. There's nowhere around this boundary that the 50 Newton force applies, and so it doesn't appear in this free body diagram. It will appear in the free body diagram of box 2. Okay, so free body diagram of 2. We have the weight, M2G. We have a pushing contact, N2. And then we have the 50 Newton force on the right and a pulling force on the left. So the 50 Newton force is here, and the pulling force is here. One thing to notice is that the same, we're always going to assume these are weightless, the same weightless cable applies the same force magnitude to every object it's connected to.
cable were to have weight, would it just be treated as having like a 1 kilogram weight in the middle of the cable, or would we have to do something else special?
At every, you would have to first choose what you're isolating, and then you could, at that point, you could figure out how much mass of cable is in your isolated piece and apply it then. Yeah. It can get a little complicated. There's a lot of, you can do it with integration, you know, it's sort of calculus heavy. But in most of the application, like cables are useful because they can sustain so much force. Cables and strings and everything, they can produce so much force compared to the mass that they have. And so in most applications, treating it as weightless is pretty reasonable. Even if the weight can be big, like if you picture a cable in like a shipyard or something, those things are huge, you know. But they're holding up such gigantic forces that compared to the forces they're sustaining, the mass is negligible. Okay, so let's do an example problem. So let's say that we have a 5 kilogram cart attached to a 2 kilogram cart. And there's a 20 Newton force pulling to the right. So first, what's the acceleration of the system? And second, what's the force applied to the 5 kilogram box by the 2 kilogram box? Okay, so go up to the board and see if you can work through part A. Okay, so there's the outline. I'm going to treat the weight as a single weight, but you can do it as a weight coming from each of these. The total mass is 7, so this is 7 times 9.81, 7g. That's 68.67. And then I'll treat it as a single normal force. That's not coming into this problem anyways, so I'll just say there's a pushing contact from the combination of all the wheels of n. And then going around the boundary, the only other contact is with this 20 Newton force. So Newton's second law says 0n plus 0 negative 68.67 plus 20, 0 is equal to 7 times, what do we know about the acceleration? Yep, only horizontal, so this is the acceleration vector once we figure out what that variable a is. And we can use the first equation. 20 is equal to 7a, so a is equal to 27ths, which I think is like 3.27. What?
It's 2 and 6, 2 and 6 sevenths, not even 8.
2 and
is basically pi.
yes.
It can't be less than
2 and yes, you're right. It is 2.857 meters per second squared, and so then you can plug that into the acceleration vector, and you get 2.8570. Okay, so for part B, we want to calculate the force acting on the 5 kilogram. That's what I said, right? Force applied to the 5 by the 2. Okay, so what are we going to isolate? What are we going to do our free body diagram of? The 5. Okay, so it looks like a lot of people have already done it. But if you haven't done it, see if you can do step B. Draw the free body diagram of the 5 kilogram box, and then go through Newton's second law. Okay, so we're going to isolate the 5 kilogram. You owe me more minutes. Be quiet and listen. You owe me more minutes. You owe me that. Okay. All right, so 5 kilogram box. So there's the weight, 5G down, or 49.05 if you multiply it out. There's a pushing contact up. I'll call that N5. And then just going around the boundary, the only other place there's contact is at that cable. So that's a pulling contact, which means it's going away from the chosen body. And Newton's second law then says what's the vector representation of that weight force?
-49.05. No, 0,
-0, -49.05, yep. Plus 0 and 5 plus T0 is equal to the mass, 5, times the acceleration vector that we got before, 2.8570. This vector is the force on the 5 by the cable. That's what we're trying to find. And in order to find that, we need to figure out what that variable t is. So the first equation says t is equal to 5 times 2.857. What do you get if you multiply that out? Oh, I got it. 14.285 newtons. And so now you can plug that variable back into the vector, and you get that the force on the 5 by the cable is 14.2850 N. And obviously, calculations like this can be useful if you're trying to engineer, try to figure out what equipment is going to be necessary for the system you have set up. If you have different thicknesses of cables, they cost different amounts of money. You don't want to use stronger equipment than you have to because it costs more money if you're working in a company or whatever. So you do calculations like this so that you can figure out what the requirements are going to be for the equipment that you're using. Okay, anybody have any questions about that? Remember, so I'm going to put it in assignments for this week so that you have time to do it. But remember that on Friday we have our first lab exam, and for that lab exam you're going to need to be able to do the kind of problems that we did in those labs. Your question?
Wait, is it not on Thursday? Was online Thursday?
The lab exam on Thursday?
Yeah.
I guess that's a mistake. Let's.
So those we were knocked out for this Friday? It's just in the lottery.
That's why I was going to do it, wasn't it? Let's. Okay, let me think about that. I'll put it on D2L today.
Okay.
And then,
Yep.
we go up to the lab, and for the lab exam, and just stay here.
You know what? Let's just do it the way it's written. So I was thinking it was Friday, but let's do it on Thursday in here. Okay? And then we'll have lab like normal on Friday. Yep.
Morgan.